Well, we want to go from thinking about the horizontal stuff to, well, I'm not actually moving mainly in horizontal and vertical directions. Like, I'm moving around this thing. And you may recall, at any given point, right, my velocity at this point, it's going off on a tangent. Like, literally, it's going off on a tangent, right? So I don't want to think about the up-down. I want to think about how they relate to round and round, okay? So the first thing I'm going to do is I'm going to illustrate these two forces onto this diagram. Here's a point, okay? And I'm going to put the x force, well, it's going to be going in this direction, okay? The reason why it has to be this direction is because if I'm on a Cartesian plane, you know how usually in a mechanics question, forces, all that kind of thing, we kind of decide, oh, I'm going to make positive this way, or I'm going to make positive this way, or whatever. But once you're on a Cartesian plane, positive and negative have kind of already been decided for you, haven't you? That's got to be positive, and that's got to be positive, right? So this force is facing in this direction. Now keep in mind, it's a minus sign, right? So therefore, the resultant force is actually going that way, right? But I have to draw the line this way so that the minus makes sense, okay? So this force is the horizontal force, okay? Now, I have also a vertical force, so I'm going to put that up like this. Okay. Now, I'm trying to think of this in terms of not just horizontal and vertical, but round and round. Okay. So, here we go. Cue another color. What I want to think about is there's going to be a tangent force, right? When I add these two up, there's going to be a force that's pushing me around. Okay. So, I'm going to put in sort of like a tangent axis, if you like. Something like this, I guess. That's a terrible tangent, but you get the idea, okay? So there's a force that's going this way. And then there's also a force that's kind of relative to the center, right? So it's going kind of like this. Oh, I missed. Oh, well, it's close enough, okay? So you've got a tangential force, okay? So we'll call this our tangent axis, if you like. Now, hold on a second. If this is a tangent axis, that makes sense. But what do you think you would call, what's a suitable name using the language that we know, for this other axis that's perpendicular to it? Probably the normal, right? It's the normal to the circle. You can see it's perpendicular, it's 90 degrees there, okay? So, along this axis, I'm gonna have a tangent force, okay? Let's call that direction of motion this way, it tends to be that way. So I've got my F, I'll make it a capital T. T this way, there's a force going that way, and there's also a force going this way. This is the normal, okay? I'm making positive away from the origin because it makes me further away from the origin, if that makes sense. So I've got positive this way, and I've got positive this way. Okay, so far so good. So now my question is, how do I relate these two forces in terms of these two forces? If you want to think about it this way, do you remember when we were doing volumes, right? And if you get a volume that's weird shaped, something like this. Do you remember this guy, right? So you take the hyperbola, right? And then you say, well, let's take the line y equals x instead, right? Because we can rotate it around that and we can still form a volume, right? We did that, okay? But here you could see that instead of having, well, x and y, it's not very useful to slice the shape across that way. You don't get useful cross-section. You don't get slices, and you don't get similar things, and you don't get shells. You get nothing useful. So that's why we changed it in terms of this. We call that kind of like the height axis, right? So we're doing exactly the same thing here. We're converting horizontal vertical into tangent and normal, right? So what we're going to need is some trig. Cue color number 3. All right. So for instance, let's just think about this horizontal force. Can you see that the horizontal force contributes some to the normal and some to the tangent? Okay. And you can show that with some fancy triangles. Okay. So here we go. I've got this. And I've got this. Okay, so what have I just drawn in red? What I've just drawn in red is how much of the horizontal force contributes this direction and how much of the horizontal force contributes this direction to each of these two new axes that I'm defining. Okay. Now, in order to convert from this to realize, okay, part of it's over here and part of it's over here, I'm going to need some trig to help me. Okay. So we already know that we're defining theta, right, as your angle around and around and around, right? So that would be here, I guess. There's theta. Okay. At the same time, I suppose, even though it's not super relevant, but we're going around in this direction, right? And that angular velocity, that's omega. Okay. So I've got that going forward. Okay. Now, if that's where theta is, where else is theta up here that is useful to me? Then have a look. Okay. Now keep in mind you've got an x-axis here, and then you've got the force in the x direction. So these two lines are parallel. Does that make sense? Right. So therefore, where do you see theta? Where's theta? Now, I can see people pointing. It would help if I had some letters here, right? And the textbook, in fact, does put letters. It's like, you know, A, B, C, D, E, F, G. You know, I'm avoiding putting those on because the diagram just kind of dies when you put all like 100 letters on there. I think you can see there's corresponding angles on parallel lines. So I see a theta there. Does that make sense? Okay. Now, that means that I can work out what this force is over here. Okay, because what you've got is, I've formed some right-angled triangles in here. You've got all these forces that are perpendicular to each other. That's why I'm resolving them. Okay. Now just have a look in this little triangle. Have a look in this little triangle. I'll just draw it over here if you like. Okay. Now you've got the horizontal force going this way. So this side has this length, right? Because remember, the length of this is important. It represents how much force there is. If it was little, it'd be a very, very small force. Okay. So that's Fx, and I'm trying to find out what this is, right? And I've already determined through trig that through geometry, that that's theta. How would you express that side, that force? Question mark? I've got a right angle triangle. I can just use right angle triangle trig, can't I? What's the ratio that relates these two sides? It's cos, right? Cos of theta is adjacent on hypotenuse, right? So therefore, this unknown side, which represents this force along the normal direction away from the origin, right? That force is Fx cos theta. That's the part of the horizontal force that's going in that direction. Okay. So let me put that in color. Fx cos theta. Okay, that's good. But I'm not done yet. I want to know about the part of this, because there's another part that's going in this direction, along this tangent axis, right? How am I going to work it out? We use corresponding angles to get from here to here, right? What else can I use? Look carefully. I can do, surely I can do some alternate angles as well, right? Because all these things are perpendicular, parallel. It looks to me like I have a theta here. You see that? Alternate angles, there's your Z for Zorro. Okay, so I can do the same thing. I can replay it. I'll save you a bit of time. You're gonna get Fx sine theta in that direction. Okay, you can draw yourself up a new triangle just like this, but it's not that hard to see. Okay.